Today we're at the workbench with our Macintosh SE30 from 1989 once again. Today we're looking at an accelerator card. There's nothing actually wrong with this particular accelerator card, but the electrolytic capacitors on it are more than 20 years old and they can use changing, and we're going to look at that today. Here is our DiiMO accelerator card close up. We can see there's 1, 2, 3, 4, 5 electrolytic capacitors that we are going to replace, and I've already desoldered one of them here. We can see that it says 22, and then the second row 6A, and then at the bottom there's a manufacturing lot number. We can see those markings even more clearly on our microscope here. Now we know that the 22 on the capacitor stands for 22 microfarad. The 6A decodes to be 6.3 volts. So what I did is I put in those keywords into Mauser. You can also do DigiKey if that's your preferred electronics vendor, but I tend to buy from Mauser. And looking up those capacitors, SMD type, which is surface mount, tolerance 20%. I'm going to assume it's 20%. I don't know. I don't know who made the stock capacitors. I don't know their life rating, if they're rated at 1,000 hours or not, but going back 20 years, I'm going to assume they were either 1,000 or 2,000 rated. Almost definitely 20% plus minus tolerance. So we've got a list of capacitors here that qualify to be drop-in replacements, and I could use them if I so choose. We've got Panasonic, Nichicon, we've got Worth Electronics from Germany, but I did not opt to buy the same type of capacitors. Why not? Because there are better capacitors. And what I mean by that is better in terms of what we call ESR. ESR is the equivalent series resistance of the capacitor, and that is, well, whenever you buy any capacitor, you get a free bonus little resistor in series with it, or at least the equivalent of it. The problem with these fluid-filled capacitors is that after about 15 or 20 years, now I'm talking about very tiny, physically small surface mount capacitors. I'm very well aware that some of the big capacitors from the 1930s and 40s, they're still actually going strong. There's these particular surface mount tiny capacitors, for whatever reason, they leak a lot. And if you are into vintage computing, you know that firsthand. So after about 15 to 20 years, these leak. Even if they don't leak, the fluid electrolyte, because of the heat of the computer over time, it dries up. It dries up and or leaks out. If it leaks out, it could eat through traces on the circuit board. If it dries up, what happens is the equivalent series resistance, ESR, that little resistor inside, there is no resistor physically inside, but the resistivity increases greatly, and your capacitance drops as well. All said, it can really harm your board in more ways than one. And I don't want to replace them again in the future, so I did not choose these for drop-in replacements, but I did pull up the specifications because, for example, here's Panasonic. We've got 6.3 volts, the rated voltage here. Capacitance, 22 microfarad here. This is plus minus 20% tolerance. And then we have something called tan delta here. This is the DF, or dissipation factor, on the data sheets which do not tell you ESR, equivalent series resistance. They usually give tan delta, or the dissipation factor. And we can see that that's 0.26 here. Endurance for this particular capacitor is 2,000 hours. This is probably a little bit better capacitor than the stock capacitors, but nevertheless, I'm going to assume this as my base. So when I pull off the old capacitors and test, I'm going to see how much it deviates from this. Also, I did Nichicon as well. Same capacitor, just different brand, and we've got the tangent of loss angle tan delta. 0.26 in parentheses is the maximum it will be for 6.3 volt capacitors. So this 0.26 is the same as the Panasonic, so I think it's a good frame of reference to use when I test my capacitor. So what did I do? Did I buy something that's A solid electrolyte? Yes, I did, but I did not choose tantalum. You might say, why not? Well, if you search for burned tantalum capacitor for Google Images, you will find out why. Take a look, folks. Yes, tantalum capacitors, unless they're some new fancy hybrid, and usually those cost more too, unless they're a hybrid tantalum, if they're a solid traditional tantalum capacitor, if you get a voltage spike above the rated voltage, for example, if this is a 10 volt rated capacitor and you get a voltage spike of say 12 volts, 16 volts, it could catch fire. Now, it's probably not going to burn down your board or anything like that, just the capacitor itself will burn. You can see this one burned, but the one next to it didn't. Nevertheless, when it burns, that's a problem, right? And these, when they fail short-circuited. And so, how these are used on the board that I'm going to swap out is they are between the 5 volt and ground voltage rails, right? And so if they fail shorted, you're going to short 5 volts to ground. And when you do that, that means one of these traces is going to burn through. It acts like a fuse, so it'll probably save your board from going crazy. But it still takes time for a fuse to blow or a PCB trace to burn. And by that time, it's you probably harm some other components. So all said, I decided not to use tantalum. I could use the voltage derating, which is to say at least twice of what the operating circuit voltage is to be safe to use tantalum. So I'm going to use 5 volts, or the board I have uses 5 volts. So if I get a 10 volt or higher tantalum, I should be safe. But I compared with other vintage boards, and many of the tantalums are rated at 16 volts. And so I went to Mouser and I spec'd out a 16 volt 22 microfarad tantalum, and it's just barely too large. Now I could get a polymer type and all of that, but I decided to actually get something that's even better. So if we go back to Mouser here, we can see here is a capacitor called Niobium Oxide. Now these are basically like tantalum capacitors, except they will not burn, and if they do fail, they will not fail short-circuited. Great. They also have low ESR, like tantalum. They're not as low as ceramic capacitors, which are like just a couple milliohms, but they are lower than fluid-filled electrolytic capacitors, and because they're a solid electrolyte, nothing will leak out in the future. These probably will last as long as the circuit board does. 30 years, 40 years, 50 years, most likely. And we can see the specifications. The ESR spec is down here. It says it's 0.7 ohm, 700 milliohms, which is quite a bit lower depending on the frequency you test at relative to the electrolytic capacitors. Even when brand new, the electrolytic capacitors are more. Now you might say, well, how do I know that? Well, I know that. I'm experienced with it. But once I start testing the capacitors with my ESR meter, I have an LCR meter that can switch between ESR and tan delta, which is dissipation factor, and all of that. So we can do a good comparison between the capacitors. We also see this is same niobium oxide capacitors here. Here's the actual part number that I ordered. Shows the case size, capacitance, voltage rating, and here's the ESR. Now this ESR, it's saying this is max, the maximum ESR, so it's not typical. It probably will be lower than this actually, at 100 kilohertz, and that's a key point here, because if you measure a capacitor at 10 kilohertz or 1 kilohertz or 120 hertz or 100 hertz, you're going to get different ESR values. And my meter, thankfully, can do all of those frequencies. And so when we actually, I'm going to show you here in a second, actual testing of capacitors, we'll be able to test at different frequencies, so you will see. But it is saying when measuring at 100 kilohertz, the maximum ESR you will see for that capacitor is 700 milliohm. So there we go. And now we will, oh, by the way, the tantalum capacitors and niobium oxide capacitors, this is niobium oxide, the little marking here is different from other capacitors like these. You can see here the negative polarity marking for the fluid filled electrolytics. The marking on it means negative. But for tantalum capacitors and for niobium oxide, the marking means positive. So if you are going to be like me and swapping out electrolytics for tantalum or niobium oxide, be aware that the marking, you need to consult your datasheet. Once you do that, you'll be fine. But all of the time, tantalums and niobium oxide, the marking usually means plus. So when we put those in, we need to be very careful, especially because you can see the case here isn't slanted in any way. We just have to go based on the marking itself. Okay, we're back at the bench and we're going to make some measurements of ESR and dissipation factor with our older capacitor and the newer ones, the niobium oxide that I just purchased. Okay, we'll turn on the unit now. And it'll default to auto. Pressing this blue button here will let us cycle through. Now it's going to measure inductance, but we want to measure capacitance. It's indicated by the CP here. It defaults to 1 kilohertz, but dissipation factor in the data sheets that we saw was measured at 120 hertz. So let's go ahead and push the frequency button. That's changing to 10 kilohertz, to 100 kilohertz, to 100 hertz, and pushing it again takes us to 120 hertz. This little button here is going to change from D to Q to theta to D stands for dissipation factor, tan delta. You remember we talked about that. So we want dissipation factor, 120 hertz. It's going to measure capacitance. So let's go ahead and do that. We have this is one of the capacitors that I desoldered. We have to be very careful because we want to make sure that the polarity is right. I have these little, this came with the kit that I bought. These tweezers here have a marking on them. So this one is negative, and this one you can see the plus, that's positive. So we want to make sure that we get the polarity correct. And also on the capacitor, the black marking means negative. So if we put our negative probe on here correctly, okay, it says it's 21.72 microfarad, which is pretty close to 22 microfarad. And by the way, capacitance in those data sheets was also taken at 120 hertz as well. Dissipation factor, or tan delta, is 0.21, and that's not bad. So this seems to be a fairly good capacitor. If we take a look at some other bits of information, now keep in mind this capacitor is 20 years old. It's also electrolytic. Okay, so if we go ahead and get the Q, the higher the number, the better in terms of high frequency. We're not going to really focus on this. It's not such a big important thing. Well, depends on your application, but the higher the number, the better at high frequencies. So if you've got a big number, the capacitor will do well at high frequencies. ESR. Now it says at 120 hertz, it's 13 ohms, which is, well, that's quite high. Let's jump by pressing frequency to a kilohertz, and we see it's still about 10 ohms, 9.8 at a kilohertz. If we measure ESR at 10 kilohertz, we can see that it's about 9 ohms. If we jump up to 100 kilohertz, we can see that it's still almost 8 ohms. So the ESR of this capacitor is quite high, and it's not really surprising. For this size of capacitor, electrolytics are several ohms anyway when new, but it really depends on the frequency that you're measuring, and we know that the new capacitor that we're going to replace with has lower ESR than this. If we press frequency again, then it switches to 100 hertz. which gives it an ESR of 14.4 ohms. But again, if we push this button here, oh, by the way, the theta, the phase angle, if it's close to 90 degrees, then that's about right. So it's a little bit off, but not a big deal. We are looking at, again, 120 hertz for dissipation factor, 0.217, 0.22, and in the data sheet it was saying 0.25 for a similar electrolytic capacitor. All right, so now let's go ahead and do our niobium oxide capacitors. We have to be careful here, make sure we've got the plus side here. The plus side is going to where the band is. So the band is up here, and I got my minus side here, so I'll go ahead and grab him. Okay, so we are on dissipation factor again. At 120 hertz, it's about 23.6 microfarads. Dissipation factor is 0.02. Now it said 0.06. If we say 6%, right? So divide by 100, 0.06 is the upper end of what it would be. They were saying this is 0.02, so we don't see any problems there. If we, of course, change the frequency and keep it in dissipation factor, then it will change things. So we don't want to do that. We want to switch to Q here, and we can see at kilohertz the Q is 11. At 10 kilohertz the Q is 1.8. 100 kilohertz it's 0.7. So I'm not an expert on the quality factor here, but the higher the number, the better it is supposed to be at high frequencies. And we go to ESR. All right, so we want to go to 120 hertz here. ESR, it says at 120 hertz, if we measure it, it's going to be 1.4 ohms, considerably lower than the electrolytic we just tested. If we go to 1 kilohertz, it is 0.6 ohms, so 600 milliohms. And if we go to a higher frequency, 10 kilohertz, 450 milliohms. Go to an even higher, 100 kilohertz, it's 220 milliohms, 0.22 ohms. Okay. So, and of course you can see that the capacitance varies by frequency as well. But really, to make sense of it all, you need to follow your data sheet and test ESR, assuming it's given, in accordance with the information that your data sheet gives. All said, the ESR of this replacement capacitor is much lower. So even though that one particular capacitor that I removed from the old accelerator board wasn't necessarily too bad, this is a superior capacitor and should have better performance on the board because the ESR is lower. We're now going to do the desoldering of the remaining 4 capacitors that are on our board here. I have a special tool that is just perfect for this, and it's a soldering station set to 350 degrees Celsius. Chances are you don't have one of these. If you do, great. You can just follow my video on how to use it. But if you don't, then you're really going to need two soldering irons to apply heat on both sides. And that's really what this is. It's just 2 soldering irons, right? You've got iron number 1 and iron number 2 here. So it's just a matter of applying heat to both sides, which is not at all difficult. And it comes right off. We don't really have to worry when putting the new capacitors back on because each capacitor is marked with a plus where the plus is supposed to, or the positive side is supposed to go. And the capacitor that you have to be careful with, you don't want to melt your connector here. You have to be a little bit careful with that one. Now we'll take our desoldering wick and clean up all the pads before we put on the new capacitors. So the wick just siphons away the existing solder and makes it nice and clean. We'll get our replacement capacitors. Now the polarity, there's a plus. You can see here on the left side there's a plus here. So we want to make sure our polarity is correct, and it's marked, the plus side is marked with a stripe on the top. And we can see that we have plenty of pad space on either side of the capacitor. It's not going to be a problem. And we can see on the microscope here that he's nice and centered, which is really important because there's a fairly small gap between the pads on either side, and you don't want to solder with him shifted over in such a way that you end up shorting both pads together. We'll do a check after we've done the soldering just to make sure, but the microscope shows that we've got him centered just right. And here's the finished board with all 5 capacitors perfectly soldered in. And we'll now go ahead and put him inside the SE30 in the PDS processor direct slot. I now have the mouse, power cord, and SCSI terminator plugged in, which is needed because unfortunately the internal drive, I lost the terminating single inline resistor blocks, so I need to plug in the external to make me be able to boot off the internal. But anyway, we can now start it up and do some benchmarks. Okay, so we've got some utilities that we can run. We've got Norton Utilities, which has a program that will do the benchmarking. It's called System Info, so we'll do that now. We see we've got the 68030 running at 50 megahertz. We've got the 68882 FPU. We'll go ahead and run this. And that's fine. Here we go. And here we are. We now see that the PowerMac 9600-200 is at the top of the list, of course, because it's a PowerMac. If we scroll down to the Quadra 840AV, which is really the cream of the crop for the Macintosh desktop towers, we see it's got a 49.5. And the SE30 with 40 megahertz 68040 accelerator running various operating systems gets about a 40. And then if we scroll down, we see the current system, and you can see SE30 25 megahertz 040. I did a test on that in the past, and I also did the same accelerator with system 7.1, which is what we're running now. I did that in the past, and we can see it here again. I ran it a couple times. So we're getting about 22. Now, this is factoring in cache speed, disk, and everything. So you might say, well, my goodness, why would I want to fiddle around with a 68030? Well, take a look at this. Macintosh 2 FX, wicked fast, right? And it's really a little bit slower than this machine now. So this is even more wicked fast than the Macintosh 2 FX.
It all depends on what you're going to compare it with. Now, if you're going to compare it to the stock Macintosh SE30 here, it's got an 8.27, right? So you're almost getting a 3 times performance boost by putting in a 50 megahertz 030. So we'll go ahead and quit out of here. Now we can see that we have some control panels that will allow us to adjust various things. The DiiMO has its cache on here. It's turned on, so what you're seeing is the full performance of the DiiMO. Well folks, we're now at the end of the video. I hope that this information has been useful. The only thing that I can add to the already extensive information that I've provided so far is that niobium oxide capacitors are not the perfect capacitor for everything. They're not even the perfect replacement for tantalum, in that they still have a voltage limit. You can get them in voltage ratings up to about 10 volts, but that's about it. But in this particular application, the factory capacitors were only 6.3 volt rated electrolytics, so my 10 volt replacement niobium oxide capacitors were the perfect choice. And if you have a DiiMO accelerator as well, then they might be the perfect choice for you. And if you have another board that has similar rated electrolytic capacitors, 6.3 volts or so, then you might want to give these some consideration. Anyway, thanks for watching, and I hope this information is helpful. Bye-bye.